Hey, so this is Joe, and this is the second video in the 9th chapter of Stewart's Calculus, and we're going to be talking about direction fields, or you can also call them slope fields. So, because there's so many different kinds of differential equations that we can't solve, and there are also a great deal that we can solve, and this applies for those as well, but slope fields are a way of kind of mapping out differential equations graphically. Literally what it is it's a graph of a bunch of derivatives in a field for a given differential equation. And what they do, in addition to kind of showing us how the derivative of the equation is moving or is changing based on x and y coordinates, what it also does is lets us see how there really are infinitely many solutions to a differential equation that can hopefully all be captured by one general solution. So I'm just going to give you an example of one. So let's say we have the differential equation y prime is equal to x plus y. And so if we had to draw a slope field for this, what we do is, first off, on the AP, when you need to draw slope fields, you're not going to be drawing too many points. You're only going to be drawing a couple. So let's draw our axes. We've got x and y. We've got zeros right there. Let's call that 1. Let's call that 2. Let's call this negative 1. Let's call this negative 2. Then 1, 2. And so we're going to draw all of the slopes for this differential equation above the x-axis. And so remember, this is a derivative. So a derivative is a slope. So we're just drawing little line segments that kind of approximate that slope, or at least show us how the slope changes based on the points in the Cartesian plane. So we have x is 0, we have y is 0, we have the point 0, 0. The slope is going to be 0, so we're just going to you just draw a horizontal line right there. It's 0, 0. When you have x is 1, y is 0, you have a slope, the derivative is going to be 1. So we draw a little line like that that looks about to be a slope of 1. We have x is 2, y is 0, we'll have a slope, the derivative is going to be 2. So the slope that we're going to draw right there is going to be steeper, about 2. So we get x is negative 1, y is 0. Well, we're going to have a negative slope then, a slope of negative 1. We'll just draw a little line segment there. When x is negative 2, y is 0, we will get a slope of negative 2, and so that's just a little bit steeper. And so now we've got, what about when x is 1 and y is 1, so at point 1, 1, well, 1 plus 1 is 2, so the derivative is going to be 2, it's going to be a little bit steeper. And then when we have y is 2 and x is 1, we're going to have a slope of 3, and so that slope is going to be even steeper there. That's really ugly, but all you need to know is it's steeper than this slope. You don't need to make your slopes be exact. You just need to make, them steeper accordingly to how the differential equation is changing. So we got 1, 0 right here. We're going to have a slope of 1. We have 2, 0. We're going to have a slope of 2. So these guys are the same. These slopes are the same. That should make some sense. So we have x is negative 1, y is 1. We will get a slope of 0 right there. And then same for negative 2, 2. We'll get a slope of 0. When we have negative 1, 2, we get a slope of 1. And when we have negative 2, 1, we get a slope of negative 1. Like that. And so that's kind of how you need to approach drawing slope fields. But most of the problems on the AP that you're going to have with slope fields, you're not really going to need to be drawing them, but you're going to need to use them to identify certain things about differential equations. So right now we're going to go do problems 3 through 6. It's all kind of one problem really, on page 610 in your book. And I have that actually, a reproduction of that right here. Alright, so this problem asks us, given these 4 differential equations, to identify which differential equation goes with which slope field here. So before we do that, I just want to say a couple things about each of these slope fields. So you can draw, if you just draw an equation that follows all these slopes going through these points, you can draw basically particular solutions to whatever differential equation this goes with. But you know, there are infinitely many of them, just because, and that corresponds to the different constants that you add at the end of the general solutions. And that can correspond to other factors too. You could have multiple solutions, but really the slope field should give you a picture of really how many solutions there are to each differential equation, and you can actually, you know, basically draw each one of them out like that. So that's kind of one of the alternate purposes of the slope field. But for the problem, so when you will have problems like this on the AP, and the way you should approach them is just pick out a few select points and compare them between the graphs. So we're going to start out just dealing with this first differential equation here, y prime equals x plus y minus 1. So what's the derivative at the origin at 0, 0? Well, the derivative is going to be negative, because we're just going to get a negative 1 right there. So we need to find a slope field where the slope at the origin is negative. Well, the slope here is 0, the slope there is 0, the slope there, well, okay, so at the origin here, the slope looks to be 0. At the origin here, the slope is positive. At the origin here, the slope looks to be 0. I really only think it's at slope field 4 is where we have a negative slope at the origin. But let's try a couple more points just to be sure. So let's try a point far away from that. Let's try point 2, 2. So at point 2, 2, we're going to have a slope of 3, so a pretty steep positive slope. 2, 2, we got a steep positive slope. Alright, well, let's try negative 2, negative 2. We'll have negative 5, a pretty steep negative slope. Well, we got a pretty steep negative slope here. It's steeper than this slope here. So I think that this differential equation goes with slope field number 4. Alright, so let's move on to this one. Y prime equals 2 minus y. So this slope field only changes with respect to the y value. So that means that the slope should be the same for every value of x given a certain value of y. Well, this one, okay, so when y is, let's say when y is 3, that would mean that when x is 1, 2, 3, and 4, and y is 3, the slopes should all be the same. Not the case here, not the case here. We've already taken care of this one, but that is the case for number 3. So that goes with slope field number 3, and we can also verify this by the fact that when y is 2, the slope is going to be 0. We've got that here, slope 0. When y is above 2, we're going to get a negative slope, and when y is below 2, we're going to get a positive slope. That all checks out. So this slope field goes with number 3. Slope field 3 goes with this differential equation, sorry. Now let's try this one, the one with the trig functions, y prime equals sine x times sine y. So we've only got two slope, we've figured out that one, we figured out this one. We have two slope fields left, and they both look like they could possibly correspond to trig functions. However, for some reason this one looks a little bit more promising, because it almost looks like a sine curve. It's got the same inflection points and everything. This one could be too, but we don't see enough of the equation to really get a good idea of that. But anyways, let's try plugging in for points. So when sine is 0, we'll get 0. So at the origin, this should be 0, and at all values of y along the y-axis and along the x-axis, the slope should be 0. And we get that. But we also get that here. So that can't be the deciding factor. So let's try point okay, actually what we should do is okay, well, here's one way you can think about it. Also, at sine is pi, you will also get sine being 0. And pi is just a little bit bigger than 3, and it looks like the slope starts to get to be 0 So if this is 3, the slope starts to be 0 about right here. So that would lead me to believe that this differential equation goes with slope field number 2. I wouldn't write this down until you do number 4, but I think number 4 we'll see pretty clearly that number 2 goes with this differential equation. But number 4 is x times 2 minus y. So we're not going to do it at the origin because both of these have the slope being 0 at the origin. But let's try at 2, 2. So at 2, 2 we will get we should get a slope of 0, and we do. Let's try 0, 2. X is 0, y is 2. We should get a slope of 0 as well. When x is 0 and y is 2. Yes, and we do. On slope field number 1. We don't necessarily get that for number 2. So it looks like this is slope field number 1. So that is that problem. Thanks for watching this video. Stay tuned for the next one. We'll finish out chapter 9 with Euler's method. Thanks.